Okay, then maybe we'll start now. Okay, everyone, hello. I am Saurabh, and welcome to this familiarization program on calculus and differential equations. Maybe we'll introduce ourselves first, and then maybe you guys can introduce yours. So I am Saurabh Roy, and I have joined here first for MTech research, and then later I have upgraded to PhD. I have joined in 2020 October. So now I am continuing PhD here, and my topic is metamaterials for microwave imaging and communication. And Mayank, can you introduce yourself?
Hi. Hi everyone, I'm Mayank Chapraval. I joined here in MTech Microelectronics and VLSI, ECE department. And in my second year, I converted to PhD. And I didn't go to the research interviews as such, but anyway, I will try to help if you have some doubts regarding the interview process. Please.
Hi everyone, I'm an MTech research student in the ECE department. My topic is nanoelectronics and photonics.
Okay, so we have few attendees here. Maybe you guys can unmute yourself and speak. Do you have the permission? I'm not sure. Can you guys unmute yourself? Maybe you can write in the chat. Okay. If you can unmute, then please introduce yourself. Yeah, maybe I will speak. I'll call you by name. So, what about Karthik?
Hi, brother. I'm looking for this PhD interview, and
Okay.
my area of interest is this microwave. So obviously, I'm interested in this calculus and the differential equations. Thank you.
Okay, welcome. And next, Meghna.
Hello.
Hi.
Hello. I'm PhD applicant here, and interested in the research areas related to communications.
Right. Okay, thanks. Next, Romeo.
Yes, hello. I'm Aprameshan Gupta. I have applied for signal processing TED MTech research interview.
Okay.
And, okay.
Okay. Next, Anuja.
Hi everyone, I'm Anuja. I'm interested in interested to doing research in photonics.
Okay. Next, Dales.
Hello, my name is Talish, and I am interested in MTech research for nanotechnology. Thank you.
Okay, welcome. Next, Ronak. Ronak, we can't listen to you. Can you please speak again? We are not able to listen to you. Okay, in that case, yeah, Ronak, go on. Okay, we are not able to hear you, so we will go to Salim. Salim, can you introduce yourself? Anyway, then, okay, we'll proceed with the presentation. Yeah, so Mayank, can you see the presentation? Mayank, can you confirm?
Yes, it's visible. Put it to presenter mode once.
Yeah, I'll go. Okay, so today's topic is calculus and differential equations, and we will be presenting Saurabh, Mayank, and Lisa. So maybe I think you are already aware about this. This is the nature of the interview. I got this from the document we got from during our interview session. So this was sent to us. So as you can see, it will not involve lengthy calculations, but mostly the basics will be tested. So they will test your fundamentals so that you know you can solve the basic things, and then later you can learn from that. And also yeah, they might have already asked you about your preferred area of research, and they will ask question. Professors will ask question on that domain. And yeah, as it is like mostly the fundamental things they will test. So today we'll try to cover these topics. Firstly, multiple integrals and differential equations and vector calculus. So let's see how much. So you guys, you can also speak. Do you have any specific interest on some topic, or like we can go on with this?
Brother, actually, whichever topic that they are interested in, that is what we are interested in, brother.
Oh, okay, brother. We'll see. So these are the previously asked questions we have. These are like a few from what we can recollect. Previously, it was asked. Mostly, Lisa had some questions because she had these topics, calculus in her topics. As you can see, these were the questions. So mostly they are very basic. So normal some differential equation was given to solve, and there were like basic questions on operator D and how to, if you know the general form of differential equation, and PI and CF, like that. Those things are there. I think most of you already know about all this from your GATE syllabus and all. These are all there. So first we will try to cover some basic it down and then differential equation. Mayank, can you see the notepad?
Yes, I can see.
Okay. So guys, I will try to write some basic topics, basic maths on multiple integrals. You guys please follow, and then maybe let me know if you have some doubts in between. Okay.
Hello, Saurabh.
Yeah.
We weren't able to hear you while you speaking.
Yeah. Can you see my OneNote? I think I was disconnected in between. Yeah.
Yeah,
Can you
now
see
I
me
can
now?
see. Yeah. Can you
Uh-huh.
write something? I'll check if it's getting like this.
Okay. I think yeah. Can you see my screen? I mean the OneNote.
Yes, the screen is visible. Yes.
Okay. I'll continue with this.
Hmm.
So as you can see, these are two integrals, I1 and I2. So basically, you can take the dy part first or take the dx part first. And in that case, the variables or limits of integration will be different. But ultimately, it comes down to same, I1 equals I2. I think you know already. So, but you have to be careful about the dy and dx part. And based on that, you select the first, this y1, y2 or x1, x2. If you select the dy first, then y2 or y1 will be function of fx. And in this case, if you select dx, then you have to take x2 or x1, so which are function of fy. So we will see an example. So this you can see, this is a x square equals 4ay parabolic curve. So you want to find out the area under this curve. Yeah, is anybody saying something? So if we want to find the first case I1 in this case, so let's take the xy plot. So we want to find out the area under the surface xy as well as bounded by x equals to a line. This is the x equals to a line, and as well as the y equals 0. This is y equals 0 line. So you want to find out this portion. So in this case, so we will go by, and let's see, now carefully see the limits of the integral. So we are taking dy first. So y in this thing, you see, yeah. So this is the second part. Sorry. So yeah, this is the strip with dy, and the xy. See, x here varies by. So this section, the rightmost section here, you see, it always is fixed at 2a. The rightmost side of the strip is fixed at y equals 2a, and the leftmost side of the strip is like variable. As you go along this curve, it is related by 2 square root of ay. So it will be like, yeah, so if you see here, this one is a function of, yeah, it will be a function of y. Sorry, yeah, this will be actually, yeah. So okay, so the x limits will vary from 2 square root ay to 2a, and the y limit will vary from 0 to a. So this is the point 2a, and this is 0 0. It will vary from this to this. So if you calculate this, so it is comes to a 4 by 3. So next we will calculate for the second one. So here you see dy dx. Okay, so here this strip you see, it varies from x square by 4a to 0. So although we are taking a strip of dA, the strip dx, this y length varies from x square by 4a to 0. And x here vary from 0 to 2a. So this is the x point here, 2a. So similarly here also we go get a 4 by 3. So yeah, so that's why I1 equals I2. Yeah, maybe you guys, do you have any question on this? You can ask. So anyway, we can also interpret it like a volume bounded by, if x function z equals xy. Yeah. So other than just calculating this thing, as an integral, we can also interpret this as volume by z equals xy surface, and x equals 2a and y equals 0 line. So if you see it like this, so this surface we can say z equals fxy, and this is our domain of some x and y. So this will be the area bounded by, the volume bounded by this function as well as the x and y domain. So you are trying to calculate the volume here. So similarly, we can calculate the area enclosed by some particular curve. Let's say this is a square of a radius r. So we can find out the area under this curve, or the area of the square. Let's say it is x square plus y square equals r square. So how do we do it? It's like very easy, minus r to r, and we will take dy dx. It is the area of the strip, this continuum, this strip. So y equals, so this you can also write as, because these are symmetrical in all four quadrants, you can write simply as like this. And now if you replace the variable equals x equals r sine theta, then you can like finally get it as pi r square. If you do it, dx equals r cos theta and theta equals. So finally it comes like that. So yeah, basically the thing is like, yeah, you can take a strip anywhere and then from that you can get the area enclosed by any curve. The previous one was the area volume bounded by this particular area given, bounded by this x equals 2a, this is x equals 2a line, and this is y equals 0. So yeah, this is one type of problem and this is another type of problem. So yeah, maybe, yeah, you guys, do you have any question?
Brother,
Yeah.
one small doubt about this volume thing you were talking, right?
Yeah, right.
This volume problem, is it, I mean, is it a different problem or what? This I cannot understand. I mean, like, is this linked to the previous problem that you were talking about?
Yeah, see, it is just the interpretation, physical interpretation. So instead of saying just evaluate this integral, you can say integral, xy dx dy. But what is the physical interpretation of this? So this is this. So z equals fxy. This is a function. So this z function is given by here in our problem xy and bounded by this line x equals 2a, y equals 0. This is this surface. S is xy. This some particular lines. This is bounding the surface. So we want to find out what is the actual volume bounded by all these three lines. It's an interpretation. Yeah, hello, is it clear?
Uh, yeah, I understand why x equal to 2a, y equal to 0 thing. Where did you get this z equal to xy thing? Where is it coming from?
No, see, this was our integral,
Okay,
right?
okay, okay, okay.
Yeah, right. So this xy you can write as z equals xy. That is what I
Okay,
am
okay.
saying. Yeah, this you can take any function of z equals fxy. Right?
Yeah,
Understood?
fine, fine. Okay, okay.
Anyone else?
Saurabh, one more doubt. I mean that z equal to xy can be any other function, right? It is nothing to do with the geometry of the problem.
No, no, it can be any function. Yes.
Okay, okay. Thank you.
Okay. Okay, if not, then we will go to the next topic. So this is, Jacobian. It is a very important topic, and it's like the use of this is like this is used in many different branches. So let's see. We'll focus in this thing. So let's say we have our x and y. It's a function of u and v. Okay. So x and y are two variables which are functions of u and v. So u and v are independent variables. And x and y are functions of that. So sometimes we have to do a change of variable, right? From xy to uv domain. So how do we do that? So there we need the Jacobian. The Jacobian is said as Jacobian of xy with respect to uv is given by Jacobian of, it's written like this, or just j, or also dou xy by dou uv. And the ultimate, this is written as a determinant del x del u del x del V and del Y del E del Y del V. So this is a determinant. So this determinant is called Jacobian of xy with respect to uv. And this xy can be any variables. Let's say xy, z, a, b, c with respect to u, v, w, anywhere. So it has to be a determinant. Remember that determinant means it's a square matrix. So how do you do this change of variable thing? Let's see. Say x equals alpha of uv and y equals beta of uv. These are two functions. And now let's say we have a integral like this, which has x, y. So you have to go to the other domain. Instead of xy, we have to write it to convert it to uv domain. For the maybe it will be easier in the other domain. For that purpose, we have to do it. So how do we do it? X we can write as alpha of uv and y we can write is beta uv, and this whole thing outside it will come modulus of Jacobian dx du dv. So you see from dx dy to went to du dv and mod j is written. So this Jacobian we have to calculate, and from that we will take modulus of that. It might be plus minus anything, but we will take only the value. And this area will now continue with u and v only, function of u and v. So yeah, anybody have any question on this? We will see an example of this now. Yeah. Let's say we have to convert from rectangular to cylindrical coordinates. So this, as you know, it is very vital. Most of the times we use cylindrical or spherical coordinates. Then we have to face this. So how do you do it? X equals rho cos phi, y equals rho sin phi, and z is normal z only. So let's calculate this Jacobian. So it is dou xyz with respect to dou rho phi z. That way we will have the Jacobian. So if you see, first line will be dou x dou rho. This will be dou x dou rho. So which here you see here dou x dou rho, dou x dou phi, and dou x dou z. From here we will do this partial derivatives. Now let's see what is this. So dou x dou rho will be dou x dou rho is cos phi. So dou x dou rho is cos phi. Dou x dou phi is minus rho sin phi, and dou x dou z is z. Similarly, all this also you can calculate. So dou y dou rho is sin phi, dou y Tau phi is rho cos phi. This is 0, and for z all these are 0. There is no this is 1. Okay, so if you calculate this determinant, it comes to be rho cos square phi plus rho sin square phi, that is equals to rho. So, and similarly, modulus of this determinant is also rho. And so if we have an integral like this in xyz domain, and let's say we have to convert it to rho phi z domain, so we will go to like this: rho cos phi, rho sin phi z. So there xyz we have been converted to this xy function, and here dx dy dz also will convert. See, dx dy also, if you can like so yeah. So here if you see, so here dx, if you get, it will be rho d rho, and dy will be like d phi dz. So dx dy d phi dz, that is the volume. Yeah, so this volume in this domain, it can be written as rho d phi dz. So how it is coming will come later. In another slide it is explained. So for now you take it as the volume in this cylindrical domain can be written as rho d phi dz. So this way, and yeah, this this is the so this is coming from the Jacobian here, this rho, because this was there in the equation. So this is explained as this. So yeah, so this way we can convert the integral from rectangular coordinate to cylindrical coordinate. Similarly, we can do from rectangular to spherical. So it's xyz to r theta phi. So what will be the normal relations there? X will be r sin theta cos phi, y equals r sin theta sin phi, and z equals r cos theta. So here also you can calculate the Jacobian just like that. R theta phi. So if you will get a this. If you calculate this, it finally comes to r square sin theta. So this we will use later. So similarly, the integral like this, f x y z dx dy dz can be written as f of. So this will be x will be written by r sin theta cos phi, and this the other terms also will be this, and the mod Jacobian will be coming here, r square sin theta. This will come, this is modulus of Jacobian, and we will take dr d theta d phi. So this dx dy dz is like this. This is the volume term. Yeah, so this is the part for Jacobian. You guys, do you have any question? So our multiple integrals are completed here. Now we'll go to the differential differential equations. Yeah, maybe you will ask question. You can continue with that. Yeah, anybody, do you have any doubts? If you did not understand anything, that also you can tell me.
Hey brother, is there anything to do? I mean, do they ask questions about this mean value theorem? If you have any information about that, can you share?
No. So anybody have any question on this Jacobian? So if not, then maybe we'll go to the the slide again, and maybe Lisa or Mayank, they will cover the differential equations portion. Lisa, can you do it?
Yeah, yes. So, hi everyone. So, Saurabh, can you show the PPT? Yeah. So basically for the differential equation parts, they will generally ask you really basic question like how to solve a particular differential equation. Like you have certain types of differential equations, right? So for example, this is just an example, like solve this dy by dx is equal to y by x, and you have to basically plot the curve. So this equation, you can see it's very easy. Basically, you have to do this separation of variables, and then you integrate, and you will get this y is equal to kx. So you can basically see this is a line. This is the equation of a line. So these kind of questions will be asked from you. Saurabh, next slide. Some questions maybe in my case were asked from this integration, like you have to integrate this function x plus sin x from -1 to 1. So at first this question might seem a little bit difficult, but it's kind of tricky. Basically, if you look at this function, this is an odd function. Fx, if you take this x square sin x as fx and replace this x with minus x, so your function will come out to be minus x square sin x. Now fx is equal to minus of f minus x. So this is an odd function and your limits are from -1 to 1. So in this case, your integral will turn out to be 0. So these kind of questions will be asked from you. Like basically, you just have to be present at the moment and then you will be able to answer these questions really easily. Next slide. Yeah, so this was from the differential equations only. What is the meaning of this operator D that you see in the differential equations? So this D is basically just a notation for by dx. This is just to make your equation look simpler and much more cleaner. So this by dx, uh, yeah, so this by dx, basically you represent it by capital D. Since this D is an operator, it must be followed by some expressions on which it will operate. So for example, you have this differential equation 2d square y by dx square plus 5dy by dx plus 2y is equal to 0. If you now replace this d by dx with the d, you will get your equation like this 2d square plus 5d plus I think that should be 1. That should be 2, sorry. There's a mistake. So basically that is 2d square plus 5d plus 2 equals to 0. And then you make your auxiliary equation to get the complementary function. That complementary function will be your solution. Next slide.
Maybe you asked if anybody have any doubts or anything, any question.
Yeah, so any doubt in this part? Basically, they will ask you very simple question in this. If not, yeah. If not, then we can just move on. So one question was asked like, what would be your this general form of a differential equation? So a linear differential equation, basically your this power would be 1 for all the terms, but you can have higher order terms. So this will be your general form. This was asked like just to write the general form of this equation. Not much from this. Next slide. Then they might ask you to plot some graphs. These graphs are important because if you are going for a PhD or an MTech research program, you will be asked to analyze a lot of data. And the best way to represent your data is through graphs. So they can ask you to plot some simple graphs, like this is, for example, a Gaussian curve. They will ask you how to, basically, you have to differentiate using this graph only. You don't have to go for the numerical values, just the simple shape. What would be the simple shape for your graph? And then differentiate that again. So these things you should be a little more clear how to plot these graphs and how to basically analyze the function. Next slide. Any questions in this? Okay, then maybe next slide.
Okay. Okay, one
Yeah,
thing.
so
Yeah, Lisa, one thing. So please, guys, remember that these questions were actually asked in the interview. These are not simply taken from somewhere. These are asked questions in the interview. Yeah, continue.
yeah, so one more question was asked. You had this particular integral and complementary function table sorter. Like how do you for whatever function you are given, how do you find the complementary function and how do you find the particular integral? So they may ask you for different functions, what would be the complementary function, what would be the particular integral. So this part you can take a look on. They can ask for a simple case, or maybe they can just mix two functions and then they can ask how would you get the particular integral in that case. So some questions from these types might be asked from this part. And I think questions would be mostly simple. You won't have to go for too lengthy derivations and stuff. Just simple. If you are able to provide the logic, that would be more than enough. Yeah, I think that's it. I think Mayank can now take over.
Yeah, anybody else? You guys have any question? Any
Were
doubt?
there
Yeah.
any
Yeah.
were there any
Yeah.
questions on this partial differential equations?
In my case, there was no question, but it would be better if you take a look at the concepts. They might ask. We can't be sure about this, but yeah.
Okay, thank you.
Could you explain the graph which you showed previously? The graph.
Yeah. Okay. So for the Gaussian PDF, for this Gaussian PDF, you remember this curve, right? This is just a normal Gaussian PDF, if you remember. Hello.
Yeah, I can hear you.
Yeah. And what's about the
Okay. If you have to take the first order derivative, so for this Gaussian PDMS, this Gaussian PDMF, this PDF, so before zero, if you see it's a rising slope, right? At first this increases and then the slope decreases. So what is the derivative? Derivative is basically the slope of the this function, right? So if you see from, for example, there is numerical values also written. For example, from -5 to, for example, 2, if you see, it increases. This slope increases. So if you take the derivative, you should have a positive slope, right? If you go from, for example, -2 to 0, your slope slowly decreases. The function is decreasing sort of. It's increasing as in the slope will keep on decreasing. So it will go down from -2 to 0. Yeah. So now again from 0 to this, for example, 2, your slope is continuously decreasing, right? So it will go down and then again from right. Someone in chat mentioned, think about the rate of change. So if you do this, keep on seeing the certain portion of your function, you can see the rate of change. So that will be basically your first derivative. Same thing after you have plotted the first derivative, you have to do for the second derivative also. Is this clear to you?
yes. Yes.
Yeah, so they may give you like some simple function and then just ask you to plot the derivative of that function. So
One more
these
doubt.
things,
Like
yeah,
this, any other graphs that we should remember? Gaussian is very well known. Apart from this Gaussian, if you can think of any other graphs that is the very familiar that we should remember.
Basically, you don't have to remember as such. Let's say they ask you to find the derivative of some function that you don't know the shape. So initial function, you can ask them to help you with the shape. Then you can apply your own concepts of rate of change to find the derivatives. So you don't have to memorize anything. Whatever you have learned for grid should be enough.
Okay, I'll just reframe the question. I was about to ask, is there any other familiar graphs that we should remember? Like this Gaussian is okay, but this is the only thing that I know. That's what.
See, one more graph that we generally use in our branches is sigmoid function. So the shape that you remember from the Fermi-Dirac distribution. So that shape is there, then exponentials are there. So this kind of shape that we generally encounter in our theories.
Also,
Can you repeat them? What were they?
So one was a sigmoid function. Sigmoid is 1 upon 1 plus exponential.
Yeah.
The sigmoid function is the one that you get in the Fermi-Dirac distribution, basically, that function.
So another one I will add is the sinc function. So that is also very evident in many cases. That also you can look into. Yeah, so then we will move on. So one thing, this Bessel function, I think you guys are also very familiar. And for many of the solutions in microwave and maybe also photonics, this function come into picture. You know, many. Yeah, is anybody saying anything? Trying to. Hello. So I want you to just have a look at this format. So if you like have this kind of thing, x square d2y dx2, x dy dx, and x square minus p square y. So this is a Bessel function of order p. Remember, this is order p comes from this. So if you solve this, so this comes to this very popular function. Yx is a1 j of p and j of minus p. In case when it is not zero or integer. When it's zero, then this defined form is there. So these are two different formats for solution of Bessel function. So this is a very popular function, and the differential equation you can remember. I think someone's speaker is on. Is anybody trying to say anything? Or maybe then you can mute yourself.
What is that order P you were saying, brother?
If you see, it will be a Bessel function of order P. You see here also we have a P. Yeah. So all these functions, this P will dependent on this. So if you somewhere you come across this kind of a differential equation with P, so this will lead you to a solution Bessel function of order P.
Okay.
Understood? Yeah.
Okay, that is just a terminology they use, is it?
Yeah, right.
Yeah, we have seen this Bessel's function in all the cylindrical coordinates.
Yeah, right. Yeah. So in the many other different domains, you will like come across this.
Okay. There is this Legendre polynomial that is also a part of this.
Yeah,
Strong
right.
functions, right?
Yeah, right. Yeah, that also is kind of related to this, and this also you can look into.
Okay.
So yeah.
Thank you. Apart from this, one more question. These are all variable coefficients differential equation, right?
Variable coefficient. Yeah, right.
Yeah, the coefficients are all x variables.
Right.
Yeah, like this Bessel's is one type of differential equation, and
Mm-hmm.
there is this Legendre polynomial. We get it in this spherical coordinates. Apart from that, is there any other type of differential equations where there are variable coefficients that you come across?
I think other than Legendre and Bessel, there is one family which generalizes all this. I don't remember the name currently, but there is a generalized family for that. Yeah.
There is this Euler-Cauchy. I have heard this. That is also something like this, or is it different?
Maybe I don't remember it properly.
Okay. Thank you.
So anybody else? Anyone else any question? Okay, if not, so we'll go to this another thing, very interesting and useful. It's called differentiation under the integral sign. I think you know it, but still to so that you guys remember it, we will mention it. First one is Leibniz rule. So where you see this A and B, these are fixed, not variables. These A and B are not variables. These are fixed values. So here this integral itself is differentiated with respect to x. So under Leibniz rules, it becomes like this. So dou x you can take inside this, and remember it is dou x, partial derivative, not a normal derivation. So partial derivative with respect to only x, not t. So this function is a variable both x and t. We are taking only with respect to x. That's why it is dou x, and it comes inside the integral sign. And also for the variable limits, we have another equation. So the general form goes by this. Here you see a and b, it is variable of x itself. So this x and this x are similar, both are same. So in this case, you can write it by this format. So you can just take a look at this, and this thing is there. It was there also. Here also it is there. Other than that, these two things are added. So it is a very popular, and you will have it in many things, like PhD you will come across. So it's good to remember these formulas.
Is there any application that you see for this Leibniz rule?
Yeah, obviously in many of our fields we will have integration that has to be differentiated. So see, integration and differentiation is kind of like inverse operation, right? So
True.
that has to be done, and but many a times the variables are not same. Here you see here x and t, two variables. Integration is done with respect to t variable, but we want to differentiate with respect to x. So that's why how to do this.
Well, if you can just name one application that you people use this somewhere.
No, I don't remember correctly, but do you remember, guys, Lisa or Mayank? But yeah, we can like find it out later, and if you are
All
really
right, brother. All
interested,
right. Carry on. Carry
you
on.
can you can mail me, guys. Okay, so this double and triple integral form we have already looked into. So this was one example I have got from one book. So that's all. So yeah, this example also you guys see. So here we have this. We have to get the volume of this portion, say dv, and where we have these limits rho 0 to rho 1, phi and theta also we have some limits. So if you have to get this volume here for this particular example, so you see we have a rho equals 6 limit and rho equals cos phi limit. So this phi is variable. So for this, so basically this is a spherical coordinate. So you can evaluate it like this. So spherical coordinate volume is like, as you've seen, rho square. Previously we were taking r square. Here you take r equals rho. So r square sine phi d rho d phi d theta. That's all. So here if you take the limits carefully, so you will come to this solution. Okay, so now we'll go to vector calculus. Before that, maybe I will go back to the slide. So yeah, somebody have something in the chat. Okay, Karthik has added. Okay. So yeah, so we'll go to the OneNote again, and for vector calculus, we'll add some things. Let's see. Just a minute. Something is not well with this. Mayank, do you have any idea why this is happening? So whenever I try to write, it keeps sliding.
Hello, Saurabh.
Yeah. So
Yeah, are you
this.
able to hear? Yeah.
Yeah. Tell me.
Yeah,
I don't
you
know,
were
like.
saying something?
It's like I know whenever I try to write, it's. Uh-huh. So why it is keep sliding? Yeah, that is what I'm. Maybe it has stable. Let's see. Yeah. Meghna, you want to show something? Yes. Can you? I will try it again. So who is it? Meghna. Okay, you. So Meghna, you can deactivate your cursor. I will try to write. So let's quickly look at vector calculus. So three basic topics are gradient, divergence, and curl, right? So let's look at gradient. So we have a scalar function if. So for that, gradient of f will be grad f given by so you see it's like dou f dou x, dou f dou y, and dou f dou z, and here I, j and k, these are the unit vectors around in the x, y and z direction. So this is, as you can see, it's a vector. So gradient of a scalar function v f is a vector. So we will look into a geometrical interpretation also. Let's see what is the meaning of this. So at this point, let's say we are trying to, this point P, we are trying to evaluate the gradient, right? So what is the meaning? So this is the normal n. So the gradient f, direction of this is, it has direction in the direction of this normal, this unit vector, this normal unit vector is the direction of gradient in this direction, and the value of this gradient is the rate of change of this function f in the direction of n. So if you have del f del n, n is the normal at the point P. So direction is normal, unit vector normal, and the value is given by rate of change across the normal. So this is the interpretation of a gradient of a scalar function f. Yeah, anybody having any question?
Brother, here you are saying f of xyz is c, f dash of xyz is d. What is there anything you want to say there?
So this f, no, this f is a Kähler's function. This can be geometrically drawn as a f of function of x, y, z equals c. So basically this thing, this, this plot curve has been shown. You can take as a surface. This surface has been represented by f x, y, z equals c. And this f dash x, y, z equals d is another surface. So this f dash can be written as f plus dou f. So it's a little bit of change of f with dou f. So these two surfaces, along between these two surfaces at point P, you want to calculate gradient f. Understood? So this is a geometrical interpretation of the gradient f.
I'll just make a statement. See, correct me if I'm wrong. The gradient means it talks about a rate of change and it gives the direction, maximum direction. Rate of change, maximum direction. Is that right?
Yeah, but direction means you have to talk about which direction. So that's why this normal comes into picture.
Yeah, the normal vector talks about the direction.
Yeah, right. So I'm saying this fxyz is a surface. At this point P, if you get the normal of this surface, so that will be the direction. Understood?
Okay.
Every surface
Yeah.
has, every point you can draw a normal, right?
Surface normal.
Yeah, right. So this normal n vector is a normal. Normal at this point P, where we are trying to evaluate gradient.
Why would you assume that it is a surface? Why not it's just a line?
Yeah, this is a good question. But see, this f function we have calculated at del f del x x y z. So you can take as x y also. Z is just not present.
Yes. Okay.
It's a general format, right? X y z is a
Yes.
three coordinate. Yeah, right.
Okay.
Okay, then we will move to divergence. So divergence is calculated for a vector point function. Unlike the gradient we get for a scalar, but gradient itself is a vector. But here it's opposite, you see. So vector function f, right? This is a vector. But this we calculate divergence. So written as divergence f, also written as this kind of a dot product, which is given by so I, j and k as usual they are unit vectors along x, y and z dimensions. Okay, so if you write like this, it comes to be gradient of f becomes dou f dou x plus dou f dou y plus dou dou g dou y and dou h dou z, because you see this f, g and h are the I, j, k component. If you take scalar product here and here, it becomes like this. So basically this is a scalar. So although this f function is a vector, the divergence itself is a scalar. And here you see it was opposite. F was scalar, but the gradient was a vector. It had a direction as well as value. So here you see what is the interpretation of this. We'll see. So at this point P, we want to calculate the divergence, let's say, and this say is a unit cube. Okay, unit cube means all the arms are unit. So for this, it says divergence is at this point P per unit volume so it is the rate of either origin or loss of what, of fluid or flux. So here something is coming, something is going, incoming, in going, all this direction can go happen like that, right? So ultimately in this point around and surrounding unit volume, what is happening? So this either it can origin something or something can be lost. So accordingly you can write as plus or minus. The divergence sign will be plus, then we are saying something has originated at this point, and if it is minus, then something has been lost on that point. So the interpretation is, if positive, that means a source is present, and if something is lost, that means a sink is present. Okay, so these are the interpretations. So at point P, if a source is present, so there will be a positive divergence, and if a sink is present, so negative divergence. So yeah, that is it. Do you have any question on this?
Hello.
Yeah, tell me.
Yeah, can you scroll up a little bit?
Here,
Yeah, yeah. Thanks.
sorry for my handwriting. Yeah, it's not good. Yeah, do you have any doubt on this?
No, no.
Okay. Okay, if not, then we'll continue to the next topic, is Carl. So Carl is like, unlike the previous cases, here the operator is itself a vector and the output is also a vector. So let's see, we will operate curl on a vector function f, and the output will be also a vector. So in the previous case, it was not that. Either the function was scalar or function was vector and the output was reverse. So we write it like this, and the usual cross product you can write like yeah, sorry, this is not. So dot x dot y dot z, and this is the fgh. So what are these fgh? This is the component of f. If you can write as fi g j plus hk. So I, j, k are the three unit vectors and f, g, h are the components. So accordingly you can calculate the curl of this. So remember, this will be a vector, and the simple interpretation of this is the angular rotation velocity of the fluid or flux at this point, at particular point P. So as you can see, if you are like familiar with electromagnetics, so there we have both divergence and curl for electric field as well as magnetic field. So there we talk about the flux, but in normal mechanical things you can have a fluid. So we can have the similar things, fluid or flux, vice versa you can use it in these terms. Okay, so any question here? So if not, we will go to the slide again. Yeah, so as you can see, we have two very important theorems. One is divergence theorem and Stokes theorem. So I suggest you guys look into this because it's very important and it's used in our domain very much. My field is like microwave. All the electric fields and magnetic fields it's used. So as it says, that divergence, you can convert it to a normal surface integral or double integral. So the divergence means it has to be a bounded volume, right? That's why it's a volume integral. So the second part you see, this is the volume, and the volume has been enclosed by this surface. If it is a bounded volume, the outer layer of the volume is a surface, right? So it says, divergence theorem says, you can get the same value by doing a surface integral of the same vector field on that surface. So that is the divergence theorem. And similarly, Stokes theorem says, if you have a line integral of a bounded line. You see this C is the line. So this line integral, you can convert it to a curl of the same function. So this line here is bounding the surface. This curve line C is the outer layer of the surface. So this same surface, if you perform the curl of the same function, this surface integral will give you the value of the linear integral. So that's given by Stokes theorem. So as you know, these same functions, these same theorems are used in our very famous Maxwell equations to convert from differential format to integral format and vice versa. So do you have any doubt in this? Okay, then we'll next go to this thing. So Mayank, can you illustrate this thing?
Yeah. Hi.
Yeah.
So
I am allowed. Yes.
Mhm. So this basically, maybe you don't have that much interest in this topic. So this is what we use in quantum electronics lab. So basically what this means is you calculate the drift and diffusions of electrons and holes in some material. So for that also you will need this differential equation. You will need to solve the differential equation, sometimes pair of differential equation. So as this thing we have seen in the EDC in gate syllabus. So what this means is J is the current density, and basically how you calculate is you calculate the drift part, which is given by this first term, which depends on the electric field and the mobility, and the diffusion part, which depends on the diffusion constant and the gradient of the concentration. When you add both of these together, sometimes they will go in opposite direction, sometimes they will add up. Finally, you can calculate the current density for electrons or for holes, or maybe you can calculate them for the excitons, as we say, which are bond states. But that will be out of scope for the current presentation. So I just wanted to show that the same mathematical concepts are used in multiple of the fields that we do in EC department. So if you have some doubt regarding this, maybe you can email me later and we can discuss. Yeah, thanks.
Okay, so yeah, we'll go to the next slide. Yeah, Mayank, maybe you can get. So this is my last slide. So you guys have a look at this. The often we have this our divergence curl and gradient in x, y, and z. That means rectangular coordinates. But mostly we use other curvilinear coordinates. It might be cylindrical or spherical. So how do you convert this? So this is a very general thing, and this is taken from Gravel's book. So you guys also can look into that. So basically this is the general form. So any kind of orthogonal curvilinear coordinate, how do you convert this? So normal equations are given for gradient, divergence, and curl. So how do you go to this the other coordinate, which is UVW? So x, y, z, it's not there. How do you go to UVW coordinate? UVW can be in general anything like cylindrical or spherical. Okay, so this is the format. So here this equation you see like it has this H1, H2, and H3 is used everywhere. All these three equations have H1, H2, H3, as well as this TU, TUV. So yeah. So this table you can remember because it will be very useful for you later. So H1, H2 and H3. So these three, 1 rho and 1. And similarly for spherical coordinates, 1 r sine theta. So if you can remember this table, it will be very useful for you guys. So maybe yeah, you can do this, and that's why the volume becomes the multiplication of this row. So this row, as you see, it is also the modulus of Jacobian. So here also this is modulus of Jacobian, and dr d theta d phi is the normal, the coordinate parts. So for cylindrical coordinate, here it is calculated t rho, t phi, t z. How do you do? And for the spherical coordinates, r theta phi. So simply you first take the r vector, unit vector. R vector is given by r rho cos phi is simply as xi plus. So instead of writing as x, y, and z, you write as rho cos phi, rho sin theta, and z. Then with that you have a partial derivative, and you can find out this t rho, t phi, tz. So here this will be useful. So if you have to calculate gradient of gradient of f in cylindrical coordinate, then this tu, see this functions, no, tu, tv, and tw, you can write as t rho, t phi, and tz, and then simply you can replace it here. And similarly, then these two also becomes very easy to get. If you have rho, phi, t rho, these three unit vectors, then easily from h1, h2, h3 here you can get these values. See, because cylindrical coordinates and spherical coordinates will be used everywhere extensively, so you have to go there. From rectangular coordinates to these defined coordinates, you have to go. So that's why these conversions are very useful. Okay, so yeah, I think we are in the end. Maybe do you have any question?
Brother, you discussed vector calculus, integral calculus, and differential equation. You did not say anything about differential calculus. I mean, like, are there any questions that they look for?
You mean normal differentials?
Yeah,
Normal.
differential. Like, there are some theorems like mean value theorem.
That you said, but these are like very basic. If you know the basics, those are enough.
Okay.
Yeah, nothing. They will only ask about the basic things.
Okay.
So because these topics are kind of like more advanced, so we covered that.
Okay. Thank you.
Okay. So yeah, anybody else? So yeah, from my interview experience, see, the professors will ask you easy questions and they will give you a lot of hints. So you don't try to memorize or do anything. Try to understand what they are saying, and from that you answer. So most of the times they look at your approach, how you get at that. You have to arrive at the solution somehow, not the solution itself. They will be interested. What is your approach? There will be different type of question completely, like what you might not have seen or not, these type of questions also what we have covered here. But still you can know somehow you have to think about it and approach it, the approach they want to see. So yeah, anyone?
Thanks, Saurav. Thank you.
Yeah, welcome. So anybody else, anything? So Sunny has asked, can you give an example where a function will be given and will be asked to plot the graph of? Yeah, that we have already shown you, no? So I think you have joined late then. So there is one, plot where Lisa have talked about the Gaussian curve and its derivatives, first order and second order derivatives. So yeah, maybe I'll go to that once again for yours. Yeah, so this was the slide for Sunny.
Hello.
Yeah.
Sir, like I was asking, like other than any Gaussian curve, like some other kind of equation they will give, and from
Hello,
there they will.
hello, hello.
Hello. Yeah. Yeah.
So basically, what they might ask is simple exponential functions multiplied by some other simple functions. For example, plot the graph of x ln x. How would you go
X,
about that?
oh, X
Something
ln
like that.
X.
For example, this is the function and they can ask you to plot that. So they will ask like simple functions. They will mix 2 or 3 functions and then they will ask you to plot it. But it will be simple.
Oh,
They will give you hints also.
yeah. Yeah.
Hmm.
So, like, ma'am, like, can you show me like how we will approach for this? Like, actually, if for any
What
exponential functions given, like sin x e to the
if
power x,
you
like that.
if you know the basic shape of the function, you just
Yeah.
have to
Yeah.
multiply those 2 functions, right? If you know
Yeah.
the individual function graph, you have to multiply and then check the envelope. So you can, according to that, you can answer what will be the final this final graph. Even if you don't reach the final graph, but you show your approach, how you're approaching the problem, that will be enough.
And like how many derivative of such function will help to draw
If
that
they
graph?
if they ask you derivative, then they will give you some simple function that you are able to plot.
Oh, yeah.
Yeah, don't
Okay.
worry.
Okay. Yeah. Thanks.
Okay. So anyone else? Anything? So if not, then we'll close it here and all the best for your interviews. Yeah, anyone? Yeah.
Okay, all the best, everyone.
Yeah. Okay. We'll close it here. Bye, guys. Bye.